Hello everyone. Welcome to one more live session with Suresh Trivedi ji and Ashwini Kumar Sinha ji. Today our topic of discussion is image sensors and their role in technology. So my first question is, what is an image sensor and how does it work?
Yeah. Hello. Hello.
Yes, you're audible. Yes, you're audible.
Okay. Okay. So the image sensor is actually yeah, image sensor is you can say that it's a kind of optical sensor that can capture the light and give you the details regarding in form of the pixels. So actually there are different kind of the image sensor even there are image sensors that you can say as the optical flow sensor that can actually give you the data about how the optics is flowing, how the lights is flowing, and it will gives you the data of regarding how the pixels are flowing in front of the camera. And there are the image sensors that can give you the pictures or the video and different other things. So all are these different categories that came inside the image sensor, and they're basically if you go for the very shorter, very shorter definition of the image sensor, they are just a kind of optical sensors that give you the uh, image that gives the light data that falling on that sensor in form of the in digital format, and that then converted into the total, that those each of those small uh, uh, optical data, that is what we call the pixels. So each of these pixels, each of these optical data then converted into the digital format to form an image or video, whatever you think it. So basically, the function behind that is they have behind any kind of image sensor. Like this one I have here is the one image sensor, and then I have the another image sensor. So these are all different kind of camera, and all these have the different kind of image sensors. So one is the one that I have here in the hand is the optical flow sensor. So it also so all of these, and this is the core camera. So what is the optical flow sensor? It also look like the camera, and this is the camera, and then I have another sensor that called thermal sensor. So all these are basically a part of the image sensor. So what makes it different? So if you go behind the core working of all these kind of sensors, they do one thing: they captures the light and they convert that light data into the pixels, and then convert it into the image or video. So what here happening is that they capture the light. So each each sensor that what each sensor support that I have this 2 into 2 mm sensor, whatever the sensor we have. So each sensor have its own photo detectors, what we call the pixels. So what is photo detector? When the light fall on those photo detectors, very small tiny pieces of photo detectors. So when light falls on that photo detectors, uh, uh, its value changes, and that those photo detectors, what those tiny photo detectors we call the pixels. So larger the number of pixels, like sometime we said 40 megapixel camera or 60 megapixel camera, all are different image sensors. These sensors are 40 megapixels. uh, Camera means that there are 40, that number of pixels are there in packed in that a small amount of area, and those pixels, those photo detectors are actually converting the light into the digital format. And after the detection and capturing of the light, the photo detection, they gives the signal, and then that either we convert it into the analog format or the digital format, what we call the analog video, video, like in earlier time might have seen the analog camera where that gives the RCA input for that connect to the TV. So it either give you the analog output or it give you the digital format of the pixels, what currently we are using the digital format of digital cameras or whatever the things.
Okay, so what are the main types of image sensors used in digital cameras and smartphones?
The main types of the image sensor used in the digital cameras and the some smartphones are CCD, charged coupled devices. and it has so many features like at high image quality, better light sensitivity, and low noise level. And where it used, actually used in high-end cameras and the specialized imaging equipment. And what are the drawbacks of the CCD, means charge coupled devices? Drawbacks are it is more expensive and consumes more power and the slower compared to the CMOS sensors. Another type of image sensor are complementary metal oxide semiconductors, CMOS. And it has so many features like low power consumption, faster image processing, and integration with the additional circuitry like autofocus or image stabilization. So where we use this complementary metal oxide semiconductor, it is widely used in smartphones, DSLRs, and the mirrorless cameras. And what are the drawbacks of the CMOS? And historically, they had higher noise level compared to the CCDs. Through modern advancement have minimized this difference. Another is the backlight illuminated, or BSI CMOS. So it has also very good features, improved light sensitivity by placing wiring behind the photodiodes, enabling better low light performance. And the applications is the common in smartphones and compact cameras for the enhancement low light photography. Another camera is the global shutters, CMOS type. And it has a very good capture and entire image frame at one, reducing motion articles. And it is used in high-speed photography and the industrial imaging. So these sensors vary in the performance, cost, and the suitability for different applications with the CMOS and BSI CMOS. So dominating the consumer market due to their versatility and the affordability. So this is the four types, basically four types of the cameras are available: CC and CMOS and BSI and the global shutter CMOS. That's all.
Okay, so what is the difference between CCD and a CMOS sensor? Should I repeat the question?
Yeah.
What is the difference between CCD and a CMOS sensor?
Yeah, I want to take this question here. So the CCD stands for the charged coupled device, and the CMOS stands for the, like in the name, it's the short form of complementary metal oxide semiconductors. So there are these are the two different types of image sensor that is being used in the camera, and both basically do the same thing. They convert the light into the electrical signal, but the way they work is the different. So in CCD, is each pixels is charged. Each pixel is charged due to the light and being captured by the photodiode and then transferred across the sensor to a signal readout register that often located at the edge of the chip, and then uh, this transfer, once the transfer is done sequentially, where all the charge from the particle is moved through the sensor, then that forms the whole image. This is how the CCD, the charged coupled device, that's why we call it charged. That because they works on the pixels charging due to the light intensity, and that being captured by the photodiodes. And then there is another sensor that we call is the CMOS sensor. So each pixels has its own photodetector and the amplifier or you can say the transistor, which allows the pixel independently capture its process of light. So one is being charged, one is being like directly been detected by the photo detector. So you can see here each pixels as here. 1 minute, let me show you. So actually you can design this sensor by your own, very low pixels quality, very low quality sensor by your own. So these are the photo detectors. Okay. These are the photo detectors. They are the photodiodes. Okay. Or these are the LDRs. Okay. These are the LDR. So what happening behind this camera lens, what happening behind this optical processor or this camera lens is they contain all of these small photo detector, these small photo detector in very, very tiny size. They are this camera and this photo, basically both have the same thing, but they are in very small tiny sized. So you can, how you can design your own camera, I'm telling you. So very low cost and very, very low pixels, very rough raw camera that you can design by your. So just take this kind of photodiode, and arrange in the array. Arrange in the array, one photodiode here, then another here, arrange in the array. Okay, arrange in the array. A lots of photodiode in this size or that size, whatever the size you want. And then the output of each the photodiode, then convert that, connect with the LED. So whenever light is falling, the LED intensity will glow accordingly. So when you move the hand over it, these pixels, whatever the photodiode combination array that you have made, when you move the hand, you can see the image in the array of same LED that you have built like this. You can see this thing on the YouTube video. Search the raw pixels using photodiode and LED. You can see the video how it's works. So basically, this is how we have made the camera. We have made the very raw, large size camera using this photodiode. So we just put, what we do is put repetitive number of this photodiode in an array to row and column wise, and then connected that with the LED in the back end. So whatever the light intensity falling, the LED intensity will also change accordingly. And when you came in front of that photodiode, and the light whatever the amount of light that is being reflected of or been obstacled by you, that will show in the image, because LED intensity also change. So that's what happening there as well. So only difference is between the CCD and CMOS is the CCD is the charged coupled device that gives the photo detection using the photodiode when it is being charged by the light. Another one is direct detection that uses the transistor to amplify the signal from the photodiode and then convert it into the digital signal. That's the only difference. So if we compare with the power consumption for the CCD and CMOS device, then the CCD are power hungry because there is a transfer of charge. Their pixel need to be charged. So that's why they are power hungry. If we go for the CMOS, go for the image quality for the CCD sensor or CMOS sensor, then CCD gives you the high quality of image because they generally produce the better quality, and there are very low number of noise in that. But if we compare with the CMOS sensor with the CCD sensor, their image is low quality, and you face some kind of noise. You sometimes you've seen that there are little bit dots, some noise kind of thing, some mosquito kind of thing you've seen in the image where there is a dark. So that is what happening. You face some kind of noise in the image in the CMOS sensor. And if you look at the speed, then the CCD sensor are little bit slower because it must be get charged to move out the pixels and to change the register value, read out register value. But in the CMOS sensor, it is faster, and it will give you better pixel readout. So both have its own own pros and own level of cons. So you have to design your camera. You have to select your camera on the basis of whether you need a fast noisy image or better clear but slower image. So you can, but you can also tweak with the software as well. there are lots of software and AI integration can be done on that. And then let's compare both of them with the cost of integrations. So CCD camera are more expensive than the CMOS camera, and their process of manufacturing of the CCD sensors are a little bit, costly than the CMOS. That's why it's happened. So, and let's compare with the size and the form factor. So CCD camera are a little bit worky because they require more space and external electronics, and they are been complex design. I have told you their manufacturing process is a little bit complex than CMOS sensor. But yeah, that is the case with the CCD. They are bulkier a little bit, but it gives you the good quality of image. Yeah, and then CMOS camera is a little bit smaller. And if you look at the durability, their CCD is less durable, CMOS is more durable. So this is the comparison from the image quality. So let me conclude the whole comparison of the CMOS and CCD. So for the CCD, image quality of is higher. You have higher power consumption at the same time. It is slow due to the charge transfer mechanism. It's more expensive. It's bulkier. It's less durable, and it's generally being used in the scientific and medical imaging. While CMOS sensor gives the good quality but lower power consumption, good quality, lower power consumption, fast due to the independent processing, more affordable, smaller, durable, and widely being used in the consumer electronics like these phones, or here be used in the designing or whatever the things, the normal camera designing or DIY kind of things. So this is the thing. Yeah.
Okay, so what is pixel resolution and how does it impact the image quality?
Actually, uh, pixel resolution refer to the number of pixels in an image, typically expressed in width into height. For example, 1920 and 1080 are as the total pixel count in megapixel, that is a 12 MP. It represents the level of the detail an image can capture. So actually, what is the impact of the pixel resolution on image quality? Actually, it is a higher resolution images have more pixels aligned for greater details and the sharpness. And the higher pixel also particularly noticeable when zooming in or printing large format images. And the image size, when higher resolution results in larger file size due to the increased amount of pixel data. Larger images may require more storage and the processing power. And when we are talking about the scaling and the cropping, the higher resolution images provide more flexibility for cropping and resizing without significant loss of the quality. And low resolution images may appear pixelated or blurry when scaled behind their natives and size. And when viewing device, the benefit of the high resolution is the best appreciated on high resolution displays or when printing. And on the small or low resolution screens, the differences between the high and the low resolution may be less noticeable. And when we are talking about the low light performance, a trade-off, the higher resolution sensors may have a smaller individual pixel, potentially reducing light sensitivity and increasing noise in the low power condition, unless compensated by the advanced technology like backside illuminating or pixel binning. So in brief, we may say that pixel resolution significantly affect image quality, but it should be balanced with the factors like lens quality, sensor size and the intended use to achieve the best result.
Yeah.
Okay.
I would like to
Mhm.
add a few things to the Suresh ji, what you have
Yeah.
said. Like what you have said, it's when you want to understand the resolution of any camera or any lens in very short and very layman thing, in a very layman language, you can say that if I'm saying there is a 12 megapixel camera and there is a 5 megapixels camera, so what does it mean? It means that it's when I say the 12 megapixel, then in that small site there are 12 millions pixel. That is the 12 millions of photo diodes are there present in that small size. So that is what we call the pixel. That is what we call megapixels. So if I'm saying that this is a 4K camera, so what it mean? It means 3840 x 2160 pixels are available in that small size. Okay, so the amount of the photo diodes, or amount of the pixel is, so each photo detectors or each photo diode is actually the pixels. So amount of that photo diode present in that area is the pixels. So suppose that if you want suppose that this is one of the photodiode that I have. So if I repeat this photodiode in an array of 10 into 10, 10 this column wise and then 10 this row wise. So this we can design a very basic 10 into 10 pixels of camera by our home using this photodiode, and we can simply connect with the LED. So we can see there the data of this 10 into 10 pixels. So this is how you can design your own camera as well. So what is pixels means? The amount of the what's the amount of this photodiode that is present in that. So if I am saying the 5 megapixel camera or 12 megapixel camera, then it means that it has a 12 megapixel, that is had 12 millions of pixels in that camera. We have the 12 millions of pixels there. There are 12 million photo detectors out there present in the camera to capture the light. So larger the pixel, the larger the light get captured in more detailing and with better the quality. That's why we need the higher pixel of the camera.
Okay. So, what are the key factors that influence the sensitivity of an image sensor?
Yeah. So there are lots of key factors that influence the sensitivity, that what we also call that we also what refer as ISO, or mm, the sensitivity of them can like we have told you earlier that there are two different, or there are few other type as well. So basically there are two CMOS sensor and the CCD sensors. So if we compare the sensitivity of these camera, then the factors that influence is the size of the pixels. How big is the pixel size? So if there is a larger pixel size, that is in the photodiode, the size of the photodiode, overall photodiode is very large. So it can capture the more light. So if they capture the more light, then it will automatically improve the sensor sensitivity, and it will give you a stronger electrical signal, and it can capture the more light, and it can easily be detect even in the low light condition. So this is one of the factor, the pixel size. If you have the smaller pixel size but densely packed, or if you have a smaller pixel size but sparsely packed. So what's been the sparsely packed? So I have very small these kind of photodiode, but they are not closely packed. They are at a very distance. So it is the light amount of light it is these and these support that here I can see you here support. So this is one of the camera lens. I have opened the lens here. I have opened the lens here. So this is the camera lens, and this is the sensor. You can see these pixels here in the camera lens. So when the light coming from this camera and then fall on the sensor. So if the light if this pixel size is smaller, and their sparsely packed. They are not, they are not very closely packed. We haven't placed these small photodiode one after another. We have kept the distance between them. Then the sensitivity bit decreased and a lots of light that is falling on the camera. So suppose that there is 1 pixel here, and then at the gap of the finger there is another pixel here. So the light that is falling and inside that in this camera room. So few of the light ray that fall at this sensor will give you the sensor data, and then we have the gap this, and then the another light fall it here. So this much area is being not being sensed, so it gives you the lower quality. So, but if you have the smaller pixel quality and they're densely packed, so you have a lots of small these kind of small pixels out there closely packed in the camera lens. Then what happened? Each pixel is capturing this own light. So even the small amount of light that is being entered with this lens, this camera lens, that is being sensed by this and as they are very densely packed. So even though the pixel size is not large that captures the whole light, but they are densely packed. There are 2 pixels out there to capture the same amount of light. So it will it can help you in giving you more good accurate signal and distinguish the distinguish between the two different light conditions. So the pixel size and the package is the one of the factors that affect the that influence that affect and influence the light sensitivity of the camera. Then next is the camera size. So suppose that this is the full frame of the camera. So this is the full frame of the camera that you can see, like 2x2, like 2 mm to 2 mm. So if it became more if we increase this sensor size to 3 mm to 3 mm or 4 mm to 4 mm. So like in the very high quality DSLR camera you have seen, when you open the lens out there, you can see the very large sensor. So large amount of light is being captured when the lens converts the light, and that light fall on the lens, then there is a large amount of space that available there to capture the same amount of light on the lens. So it will give you the more richer image, more accurate image, like what you see in the DSLR cameras, or in some of the wide angle camera you have seen that they give you the large image. So the second factor that affects the quality is the pixel size is sorry, the sensor size. So one is the pixel size, that is what is the size of photodiode. Then is the sensor size. So here what we mean sensor is that array of these pixels, these are small photodiode. So what is the size of the diode, the detectors, photo detectors available on the sensor, and what is the size of the sensor, both affect. Okay, so if you have the larger pixel size, or then it will capture more light and give you more richer, and then you have the larger sensor size as well, the whole array of these pixels, small pixels in the larger size, then give you, it can capture the even more light and give you the even more richer image. So this is the second factor, that is one is the pixel side, then the sensor side, and third is the architecture, the sensor architecture, the design. Like there are basically two architecture out there. One is the back illuminated BSI sensor, one is the front illuminated FSI sensor. So BSI sensor, the light sensitive area is placed back of the chip, improving the amount of light that reach to the photodiode. And in the front emulated sensor, the traditional sensor that emulated you know illumination may be influenced by the wiring and circuitry and all other things. And there are few other factors are also, out there that, let's not go into the details of them, because it takes a lot of time, because there are also different parts. I am going to keep it a little bit shorter because I have already taken a lot of time. So just few more points I'm telling about. And another is the exposure and the shutter speed. Like when you buying the camera, you have seen the shutter speed and the aperture. Aperture is the, what's it? Uh, the area from which it's the light entering. So it can, aperture can be into increase or decrease based on the, your requirement. And so that the aperture can also affect the overall sensitivity of the camera. And then the exposure, the shutter speed at which the camera shut down, like captures the light and then close and open. So that speed also affect that. And then third, and the last one is the optical quality of the lens. So how much light lens will able to convert the light into the camera lens. Like this is the one lens, and there are few lens that I have in the camera. There is the another lens of the camera, and there is the another lens. So how much light these lens able to conserve, and how much large size this lens each. So that is another thing that will, affect the overall size.
Okay, so what is dynamic range and why it is important for image sensors?
Yeah, okay. So uh, dynamic range is, if we say, if we want to define the dynamic, it's a imaging, what we can say, that range of light intensity an image sensor can capture. So uh, like suppose that it is capturing in the high contrast scene, where the light is very bright or very dark shadow, or so how sensor can act in accordance to with these different kind of scent, shades, or we call appearance in front of it. So uh, the basic, basic use of this is like how it can perform in different light scenario, like the low light condition, dark light condition, the bright light condition. There are the scene in with both there is a, dark shadow and the bright shadow. So how the camera will be able to, able to translate between all these different ranges, uh, and how these, how these handle these kind of different scenarios, the bright contrast and low contrast. This is what we call in the dynamic range. So it's ensure the footage look realistic and capture it very high lightning condition. So if we are capturing the very high lightning condition, then like when you see the HDR video in your phone, then you suddenly see the brightness of the overall screen get increased suddenly to very high level. Why? Because it want to show that the video is being captured at very highlight condition. That is what we call HDR, high dynamic range. The lightning condition is very bright in that range. So there are different kind of, the shadows, the brightening condition, the contrast of the things. All these comes in the dynamics range of the camera. Hello.
Next
Yes,
question.
yes. Okay. So explain the concept of quantum efficiency in an image sensor.
Actually, when we are talking about the quantum efficiency in an image sensor, it refers to the effectiveness which the sensor converts incoming photos into the electrons, which are the used to generate an electrical signals. It is expressed in the percentage and measures the ratio of the number of electrons produced to the number of incident photons at the given wavelength. When we are talking mathematically, quantum efficiency is nothing but it is the number of electrons generated upon the number of incident photons multiplied by the 100. You can easily calculate the quantum efficiency. And what are the basic important parameters in this is the wavelength dependence. QE, मतलब quantum efficiency varies with the wavelength of the lights. It is very important. Image sensor typically have different QE, मतलब quantum efficiency values across the visible spectrum and into the infrared or ultraviolet regions. Another notable point is the material and design. The quantum efficiency depends on the material used in the sensor and its structural design. For example, back-illuminated sensor often have higher quality quantum efficiency because they minimize light absorption and the reflection before photons reach the photo detection. Importance and the performance is also very playing a crucial role in the case of quantum efficiency. Higher quantum efficiency means the sensor can capture more light, improving its sensitivity and the signal to noise ratio. This is the crucial for the application like astrophotography, low light imaging, and the scientific instruments. For example, a quantum efficiency of the 90% at the specific wavelength means that the 90 out of the 100 incidents photons results in the electron generation, while the remaining photons are lost due to the absorption, reflections, or other inefficiencies. That's all. Next.
Okay, so what are some challenges in designing high resolution image sensor for smartphones?
Actually, when we are talking about the challenges, the designing high resolution image sensor, the smartphones involves several key challenges. For example, miniaturization and the light sensitivity. It is also playing a crucial role. Higher resolution requires a smaller pixel to the more into the sensor. Smaller pixel capture less higher, reducing image quality, especially in the low condition. And another is the optical limitation. It is smartphone sensors have a physical constraint due to the small size, making it challenge to match the resolving power required by the higher resolution sensors without introducing optional distortion. Another parameter is the thermal management. Thermal management is also very important. High resolution sensors generates significant heat during the operation, which can degrade the performance and the image quality of the not managed efficiently. Another parameter is the power consumption. It is also a very challenging task. Power capturing and the processing high resolution images demands more energy, posing a challenge for the maintaining the battery life. Another challenge is the data handling. Larger image files require higher data bandwidth and the storage stress, the device, broad wave, and the potentially slowing down the performance. Another challenge is the signal to noise ratio, normally known as SNR. Shrinking pixel size result in lower SNR, leading to the increased noise in the final image, especially in the challenge lighting condition. Next challenge is the manufacturing cost. We have to maintain the manufacturing cost also. Advanced technologies needed for the high resolution sensors, such as the back illuminated design or the stacked architecture, increase the production complexity and the cost. Another challenge is the balancing form factor and the performance. The thin and the compact design of the smartphone limits the space available for the larger sensor and the complex other lens assemblies, etc. So innovative technologies like capturing photography, better sensor material, and the AI-based image processing are being employed to mitigate these challenges and deliver high quality images. These are the few challenges which we should care.
Okay, so how does the sensor's frame per rate affect video recording quality?
Okay, so the FPS, what this FPS first, let us understand what this FPS mean and how this affect, then we will talk about how this affect the overall video quality. So the FPS means the frame per second. So FPS defines the how much frames a image sensor is capturing per second, how much individual frames are being captured by that image sensor or during the recording of the video per second. So per second, whatever the image amount of frame. So suppose if it's very high FPS, so that means it is capturing the frames every second at very high speed. So lots of frame being captured in the same amount of time in 1 second. Suppose that I'm telling that 120 FPS. So that means in that 20 seconds, there are 120 frame being captured. So what happened and how it affect the video quality? So suppose that this is a video right now you see. So if there is a lower FPS, what will happen? So here I'm moving the hand. So how you feel? At the starting, and then because it's not capturing the frame in the real time at very high speed, what it will do, it will capture one frame at the starting, then at the middle, and then the bottom. So how the image will look like, you feel a kind of jerky image. So this is how the FPS affect the camera, because few of the frame, like I am moving hand with this speed. So what it is happening, it capturing each and every frame along from this to this. So if the FPS is low, then you might see some of the frames that have been captured at the start might missed out some of the frame in the middle, and then it will show you the last frame. So from this to this, some of the frame got missed out. So it looks you little bit jerky image video like this. Rather than this smooth. So if greater the smoothness, it is capturing and translating the one frame over the other frame, translating from the from to the another frame to the another, the video becomes smooth, like in the video, if the FPS is very high, you can see very smooth translation of the, you can actually experience this while some car is moving at very high speed, or while watching the cricket or football, because if that football is captured by the very high FPS camera, you can see the smooth translation of the ball moving. You can't see the blurry, or you see a ball here and then you see the ball at the bottom. The translation between the each of these frames is very smooth. You can see the ball going from here, like from here to here. It totally, you can't miss any of the frame. Like you see the one ball here, one ball, and then last in between, whatever the frames are got missed out. So this is how it affects the overall video quality. So FPS plays very important role for the video, because it's the amount of frame that is being captured in the video per second. So if it is lower FPS, then image feel little bit jerky, lots of frames because it's being missed out. If it's very high FPS, then there be the smoother translation between the each pixel, each frames, and video feels very smooth translation from one to there. And if you are slowing the slow motion sensor, like you want to, then you need very high FPS camera, like 240 or 1000 FPS or 6000 FPS. So what they do, take whatever the frames that we missed with our own eye, we can't see. Whatever the frames that missed with that camera, that frames is being captured, because there 1000 FPS means 1000 frames are being captured per second. So you can capture each and every movement, small micro movement that is being passed from like if you want to capture the video of the bullet, or you want to capture the video of any fast moving projectile or rocket that's going very fast speed. So it might be missed out. This image is so very blurry or very jerky if there is a low FPS. But if there is very high FPS, you can capture how the rocket is going each frame by frame in very slow speed. So that's how the FPS plays an important role. If there is a low FPS, then we will see the image like this, something like this. Okay.
Okay, so what is the role of an analog to digital converter in image sensor system?
Actually, an analog to digital converter ADC in an image sensor system plays a very crucial role, converting the continuous analog signal generated by the image sensors, photodetectors, into the discrete digital data. The image sensor captures high information from the scene and generate analog voltage proportional to the intensity of the light that each pixel detects. The ADC then sample these voltages and converts them into the digital value, which can be processed by the digital image processor. This digital data forms the final image output. The ADC's accuracy and the resolution directly impact the image quality, as it determines the precise with which high intensity is represented in the digital image. This is the main process of converting the analog to ADC, digital.
Okay, so how do image sensor handle noise, and what techniques are used to reduce noise?
Yeah, so there are lots of caused of noise in the image sensor. One is due to the thermal, that is what we call the thermal noise, that is caused by the random electron movement due to the heat. So if there is a heat condition, or sensor being heat by some circuitry behind it, or being the natural environment condition, then some kind of noise being you can see some kind of noise due to the electron movement because of the heat. And there are some kind of noise either using because of the because of the one pixel of the camera is sensitive to the other pixel of camera more sensitive. So you can't make it very perfect pixels. You can't make every diode very perfect exactly like all of them. Some in the manufacturing process, or during the design, or during the whole setup, some pixels might become very sensitive, some pixels might become less sensitive. So the pixel data is being more sensitive and the pixel data is being little bit less sensitive in consecutive to that. So that creates the noise. So that is the another level of noise that you can see because of the pixel sensitivity variation. And there are different kind of other noise as well. So if as well, but these are the broadly two kind of noise that you can see. So if we want to remove the thermal noise, then we have only one option, that is the cooling, active cooling system, or somewhere we use the tech thermoelectric coolers or some kind of cooling system to adjust this and remove this the remove the electrons to move out, and that causes the noise in the signal in the end result. And then this for the sensor, the noise that is being caused due to the difference between the sensitivity, it can be tackled using the softwareically, and or also be with the high gain amplification and low gain amplification, and we can at the end we can calibrate these things and using the circuitry, these amplification circuitry, and we can the one that the pixel that is with low sensitivity, we can increase the gain of that pixels, and then we can match with the other pixels. So this is how we can do. And but right now in current scenario, we can say we are now using the AI. We can enhancing the image greatly and beautifully with the AI rather than this old circuitry technique, those amplification technique. We are using the AI to fill up the pixel, to make up with the pixels, and to reduce the noise, to beautify the image. So now AI being used, and most of the things can be done with the software. Either it's the heating, either is the noise due to the thermal, it's noise due to the pixels. All these can be being figured out and filtered out with the use of AI rather than the need of any kind of cooling and the amplification system. So all these in the next in the next few decades, or with the advancement of AI, you can simply see the camera become a little bit more thinner, and will its design being little bit more simplified, because all these extra circuitry, extra cooling things, and all those things that were being used earlier in the circuitry to refine the image are being removed, and the AI being used being used there to reduce this kind of noise.
Okay, so how does the performance of image sensor impact augmented reality applications? Should I repeat the question?
Yeah, can
How does the performance of image sensor impact augmented reality applications?
yeah. So I would like to invite the Suresh sir. Do you have anything? Then I will take the question. Anything to say on this?
Actually, image sensor play a vital. Now, question is what role do image sensors?
Yeah. So let me take the question then. Yeah. So how does the performance of image impact the augmented reality? Uh, so like in AR, what is the AR, augmented reality? It's the what it do. There are two kind. If you go in this area, there one is the augmented reality, then one is the mixed reality. So what the mixed reality will do, it's overlay some kind of things that is being in the current environment we are seeing. And there is the mixed reality. In the augmented reality, it is some kind of supported you scan some kind of image, something. Then behind the software, it will create some kind of hologram and something like that. So how does this impact? So one thing that impact is the resolution. So if there is a very high resolution and detailed sharp image, then the AR application, the augmented reality application that you make in the augmented reality from the real world, if the resolution is very high, you can train the that virtual elements with the real elements in very accurate and very high, very rich quality. The quality being very rich. If the whole, suppose that I'm making some kind of AR games that has the tree, that has the the lakes, that has the many other things out there in the world. So if I'm making those all these trees, these lakes, and everything, this simulation in the air, the augmented reality, then what I am doing to train to make those simulation from the real world by capturing this real world scenario. So if the resolution is very high, I can capture the every detail of that lake. I can capture the every detail of this tree leaves, the structure of the leaves, the veins, the xylem and phylums going on the leaves, the barks of the tree, the curves, the lines of the tree. We can capture every details because of the high resolution, and we can implement same details because the model that is being trained for that air, for the simulation, it's being captured in very detail. So when it is being translated into the air, the augmented reality, then all those detailing can be seen in the air as well. So if there is a noise in the camera, the resolution in the camera is very low, then what will happen? It will not capturing the whole details of the leaf, nor those things. So you can't see this, experience this in augmented reality. So it give you the bad, very noisy experience in the augmented reality as well, because uh, it is basically being a simulation from the real world. We have captured the scenario scenes from the real world to and make a model and then present a simulation in the gaming world. So they are actually being captured from the real world. So if, one is the resolution, second is the frame rate. So we have the higher frame rate, we have the very high, and then third is the field view. We have high field view, and we have the depth sensing field view. Then same can be translated into the AR world, the augmented reality world. And one of the main important thing is the depth sensing, the 3D mapping. So in the in AR world, why we use the AR? Why we need the AR? Here it comes. Because AR give you the 3D experience, like what we play the games, or we play some kind of stuffs in 2D in the screen. So it's two-dimensional, it's X and Y. But in the augmented reality, we can see this in three dimensions, the 3D. We can sense the depth between the objects. So if there is a tree, it has a leaf, then we are not seeing the tree and leaf in 2D. We are not seeing it as a picture. We are seeing the depth. We can see the distance between both leaves. So here the 3D depth sensing camera take place. So in augmented reality, you also need the depth sensing, the 3D mapping in the camera. So along with these kind of camera, like this camera, or you can see camera. So how do we capture the depth of the image for those scenarios? So if you want to capture the depth with this camera, so in most of the phones you have seen, we have multiple camera, one camera, two camera, three camera, four camera, some have five camera, six camera. So now a smartphone are coming with multiple of camera. So among these few camera that you've seen in the phone, each there is extra camera. So what that extra camera help you in? Sensing the depth sensor camera, depth sensing camera. So it can either be done by combining two camera, like one, I have implemented one camera here and one camera here. Like see things in 3D, because we have the one here and one here, and using the both combine, and we can overlap the image, we can create a 3D, we can get the sense of the depth of that image. There's hobby sensor. We can implement the same thing in depth sensing. We can combine two camera. We can capture the image, one from this distance and this distance, or one from this angle and this angle. Then we will overlap both of the frames, both of the pictures, and then we will find the distance between the suppose that this is the hand capture from the one camera, then one hand capture between the other camera. So then when it overlap, it can able to see the depth, the distance between these things. So so this is how we can combine two camera to capture the depth. So one depth sensing. So here is how the depth sensing camera can play a role. And there is another method that is that these camera have a depth sensor that is based on the light. It emits the light, and the light cam, and using that light, either the laser or whatever the things, or IR, it try to get the depth, the z axis, the depth of the image. So it can either be done by the combining two camera, or be done by combining one camera with TOF, or depth sensor, or any kind of radar things, and then combined with the image to sense the depth, or 3D mapping. Using the lidar, we can map out the whole things. So when we have the depth sensing camera, then we can do the 3D mapping of the whole scenario that can be translated in the AR 3D world. So that is another thing. And then other few things that will impact is the motion tracking, the latency, the sensor fusion, and the color distortion. So color distortion can be corrected with the help of a spectral sensor. So there are few spectral sensors. The spectral sensors are specialized in capturing the spectrum of light, each and every different spectrum of the color. So there are few spectral sensors out there as well. There are spectral sensor for visible light. There are spectral sensor combine both visible light and NIR, near infrared spectral, give color accuracy. So these color accuracy are actually been done by the spectral sensor. They create the spectrogram. They capture the color with more accuracy, and then they used with the camera, combined with the camera image to correct the noise, correct the difference between the two spectrums of the colors, and then they improvise and make it more real and accurate, more color accurate.
Okay, so this will be the last question of the session. So, what are some emerging trends in image sensor technology?
Yeah, so
Could you-
some of the emerging trend in this, let me handle this question, and then I will pass to I will invite the Suresh sir to also give his point as well. So there are lots of emerging trend are coming out in this camera area, in this field. One is the TOF, adding the TOF, the time of flight sensor that I have told you, for capturing the depth, TOF, or radars with this camera to sense with more depth of the image and to more accurate image. And there are few technology now being developed for the NIR, NOR, near infrared range, or near the ultraviolet range, or around that gives you the more night vision capability to the camera that being employed. Then there are few trends with the lens as well, are being done for filtering out the light. So suppose that if you are capturing the sun, so if you use the normal camera, it seems so brighter because there are lots of UV ray are there. So we have the UV ray filtration lens. We can attach that filter lens, and we can capture the sun more accurately with more depth. And there we have the UV ray filtration. We have IR filtration, infrared filters out there. So there are lots of things are there coming in the market. And then the addition of AI as well, the artificial intelligence as well. So there are lots of area. So yeah. So Suresh sir, if you also want to add some points to it.
Yeah. Few more emerging trends in the image sensors are 3D image sensing. These sensors are capable of capturing the depth information in addition to the additional 3D image. Another is the time of flight, TOF sensors. It is also playing a crucial role. TOF sensors measure the time it makes free light to travel from one place to another scene. Another emerging technology are the advanced CMOS sensors, also playing a crucial role. And next is the multi-spectrum and the hyper-spectrum imaging is also playing an important role. Another is, as you explained, AI-powered image sensors. And another is the imaging technology is the improved low light performance is also. So these are the few emerging technologies are the enhancing the capabilities of the image sensors trending nowadays. That's
Okay, okay. So this was very insightful. So, if you have any question, you can post it in the comment section of this video. We will take that question in the next session. So, thank you, everyone.